Okay, so welcome back everybody to our series of online talks. So today it's a pleasure to have Wenhao Ou, who will talk about uniruled compact Kähler manifolds. So please go ahead.
Okay, thank you. Thank you for the introduction. So I would like to thank Professor Mustada for the invitation. So I'm so glad and so proud to present my work on this online seminar. So I will talk about compact Kähler manifolds. So it is a topic in complex geometry. So Kähler manifold, it is a complex manifold X endowed with a Kähler form omega, which means that a smooth, closed, positive form, real form of 1-1 type, so 1-1 form. So the typical examples, there are a projective space Pn. So it is a Kähler manifold, and there is a standard Kähler form on it, which is called the Fubini-Studi form. And every submanifold of a Kähler manifold is a Kähler manifold because we can restrict the Kähler form on this Kähler manifold, on this submanifold. So the submanifold is again Kähler. And more generally, we can define Kähler varieties. So this is due to Kähler in 1965. So they are possibly singular complex analytic varieties endowed with a Kähler form. So again, typical examples are projective varieties. So every projective variety is Kähler. It is curious to know how far from Kähler manifolds, general Kähler manifolds, to projective manifolds. It is known due to a theorem of Razan that if the dimension of X is at least 4, then there are compact Kähler manifolds which are not approximable by projective manifolds. And even any bimorphic model of X cannot be approximated. However, if the manifold has dimension at most 3, then this statement is true. So this approximation problem is known as the Cordella problem. Indeed, Cordella proved this approximation property in 1960 for surfaces. And later, Lin in 2017 proved this approximation property for compact Kähler threefold based on the birational geometry of compact Kähler threefold. So that's what I'm going to introduce in this second paragraph. So the log minimal model programs and the abundance theorem, they hold for compact Kähler varieties of dimension at most 3. So I think this project was initiated by Campana and Piternel in the 1990s. And a breakthrough work is by Horing Piternel in about 2015. They mostly established the minimal model program for compact Kähler threefold. And then with Campana, they mostly proved the abundance theorem. And later, Das, Haken, and myself, we also do some contribution to these topics. For minimal model programs, for general analytic varieties, it is known that minimal model programs hold for projective morphisms between complex analytic varieties. So this is due to 2 groups of peoples, Das, Haken, and Paun, and Fujino. So now I'm going to talk about rational curves in compact Kähler varieties. So I recall that a rational curve is a complex analytic variety whose normalization is isomorphic to P1. So equivalently, a rational curve is the image of P1. So to find rational curves in a complex manifold, there is a very famous theorem, which is called Morris-Spann-Briggs theorem. In particular, Morris showed that if the canonical divisor or canonical line bundle of a projected manifold X is not nav, then X contains a rational curve C, such that the intersection number C dot Kx is negative. The proof used the algebraic property of projective manifold. So it relies on this method called the reduction modulo P. So this method does not adapt directly to the setting of general complex varieties, because for those varieties, we do not have algebraic structure. So to explain the word uniruled in the title of the talk, X, compact Kähler variety X is called uniruled if it is covered by rational curves. So through every point of the variety X, there is a rational curve passing through it. So Miyaka and Mori, they proved that in X is uniruled if and only if X is covered by curve C, such that C intersect Kx negatively. Later in 2004, Buxong, Paun, and Peter Niao, they showed that the later condition, so the condition that X is covered by Kx negative curves, is equivalent to that Kx is not pseudoeffective. So we will come back to this definition, pseudoeffective, a little bit later. So it is natural to expect similar properties hold for compact Kähler varieties. So for surfaces, this is known. This is due to Yao in 1974. And we remark that this theorem of Yao is even earlier than Morris Van-Brick theorem, because Yao's theorem relies on classification of Kähler surfaces due to Cordera. But much later, Brunella, in 2006, he proved that this uniruled characterization holds for compact Kähler threefold. Recently, we proved that a compact Kähler manifold X is uniruled if and only if its canonical line bundle is not pseudo-effective. So we generalized the theorem of Miyaka-Mori and Buxong, Paun, Peter Niao to the setting of compact Kähler manifold. Combined with previous works, now we know that if omega x, the canonical line bundle of a Kähler manifold, is not nav, then X contains a rational curve. So this is due to Cao and Horing in 2020. And furthermore, the Kong theorems also hold for compact Kähler manifold, and this is due to Haken and Paun in 2024. Indeed, Haken and Paun, they proved that these Kong theorems hold for generalized KLT-Kähler pair, Kähler generalized pair. So to compare with the projective side, now for the minimal model program, MMP, it remains to prove the contraction theorem. So I will note that this contraction conjecture was already raised in the theory of Kähler-Ritchie flows in the 2020s. So even before the minimal model program for Kähler threefolds. Also, there are so many works here, but for example, in a paper of Song and Tian, they show this comparison between Kähler-Ritchie flows and minimal model program with scaling. Then this contraction conjecture for general Kähler manifold was written down by Tosati in one of his papers. So I will note that this contraction theorem is known for projective manifolds by the Kawamada's base point free theorem. But here require that every class contraction, so every class we are looking at, they are rational class, which means that they come from line bundles. But for transcendental classes on projective manifolds, this contraction theorem was also recently proved by Das and Haken. Now I would like to give a short sketch of the idea of the proof of this uniruled criterion. We follow the method of Brunella. So I consider X as a compact Kähler manifold such that omega X is not pseudo-effective. And this is the difficult part. So we need to prove that if omega X is not pseudo-effective, then X is uniruled. So thanks to Miyaka, Mori, and Buxong, Paun, Peter Niao, we may assume that X is not projective because if X is projective, this is proved. So here, an important remark is that by Cordell's embedding theorem, if X is compact Kähler but not projective, there must be some holomorphic two form, sigma, which is non-zero. So this is independent of the condition where omega x is pseudo-effective or not. This is just because X is Kähler but not projective. To see this, we see that Cordell's embedding theorem says that X is projective if there is some rational class, which is rational cohomology class H2, which is a Kähler class. But if there is no two form, then by this Hodge theory, the H11 is exactly equal to H2. So by the openness of Kähler cone, there must be some rational Kähler class in H2. So we will look at this two-form sigma. So we can consider this contraction with this two form. It defines a morphism from the tangent bundle of X to the cotangent bundle omega X or omega 1X. So I will let F be the kernel of this contraction. Then F is a coherent subsheaf of tangent Tx. We first observe that F is different from Tx. This is because this two-form sigma is non-zero. Moreover, we claim that F is not zero. Indeed, if F is zero, this means that this two-form is generically non-degenerate, meaning that this two-form sigma is generically a symplectic form. So we can consider this. So if you have a non-degenerate non-degenerate symplectic form, then the underlying dimension must be even. So we can consider this self-wedge product of 1 over 2 dimension X. And this will define a section of omega X, which is a contradiction because we assume that omega X is not pseudo-effective. So to visualize this argument, we can imagine the case of symplectic, holomorphic symplectic or hyperkähler manifold. So there is some non-degenerate symplectic form. Then in this case, we know that the canonical class is trivial. So this is the reason why F is not zero. So we have a subsheaf inside X, the tangent Tx, which is non-zero and which is not Tx entirely. So it is something in the middle strictly. Now we observe that since X is Kähler, the Hodge theory implies that sigma is a closed differential form. So we can use this Cardan calculus to show that F is a foliation on X, which means that F is closed under Lie bracket. Now we will use the method of Brunella, who proved the theorem in dimension 3. So in dimension 3, this F must have rank 1, because it is between its rank is between 0 and 3 strictly, but it is the kernel of two form. So it has rank 1. So 1 plus 2 is equal to 3. That's why it must have rank 1. Then a simple computation shows that this F dual, F star, it is a non-pseudo-effective line bundle. So if we consider pseudo-effective as some positive notion, then we can write this. So the F star is kind of negative. And Brunella showed that the closure of this leaf of this foliation F, they are rational curves. Indeed, Brunella classified rank 1 foliation in compact Kähler manifold. So in particular, we can show that F is induced by a meromorphic map or rational map from X to some Y, with Y is of dimension 2, such that the two form sigma is indeed from Y. So the pullback of some two form on Y. and f is the relative tangent of this rational map. So this is the situation of dimension 3. So in higher dimension, which is the case we focus on this talk, so it is now this f is in general a higher rank reflexive sheaf. So usually it is not easy to talk about its positivity. So our method is to take some maximal day stabilizer f prime. Then we can show that f prime is a foliation, and we can talk about its positivity or negativity. Indeed, we prove that the dual f prime star is non-pseudoeffective, reflexive, coherent sheaf. So for short, I denote f prime star is negative. So which is the same kind of the same assumption as in the situation of Brunella's proof. Now the following is the key step of the proof. We show that this f prime, this foliation, is induced by a meromorphic map x to y. Equivalently, up to blow up x, this morphism will become this rational map will become a morphism. So, and the two form sigma comes from y. And the reason is that the f prime is the kernel of this contraction with the two form. So that's why so we can imagine that this two form must be 0 on the tangent on the vertical direction of this rational map, because this vertical direction is just the foliation f. So the two form must come from the base y. So when I was trying to prove this theorem, I cannot prove that the leaves of this foliation or the fiber of this rational map, they are rationally connected or uniruled. But later, this was proved by Cao and Paun. So once we have this key step, we can boil down our variety or manifold X into two pieces of a smaller dimension. One piece is the base dimension, the base Y has dimension between 0 and X. The other piece is the fiber, a general fiber F of this rational map. Once we have this additional structure, we can use induction by dimension to conclude the uniruled criterion. So this is roughly the proof, but I would rather skip this part for now and focus on the key step, meaning that once we have this condition f prime star negative for foliation, then the foliation is induced by meromorphic map. So if time permits, we can come back to the precise statement to see how we can use induction by dimension to prove the uniruled criterion. Okay, so let us briefly recall the notion of foliation. A foliation F on a complex manifold X is defined as a saturated coherent subsheaf of the tangent bundle. Saturated means that the quotient Tx, quotient by F, is torsion-free. And we also require that F is closed under the Lie bracket. To be precise, we need to check that for example, we can check that on the locus where F is a subbundle of Tx, on this locus, F is closed under the Lie bracket. Now there's a very typical example of foliation, which is given by the relative tangent. So consider a surjective morphism between complex manifolds, F from X to Y. Then the relative tangent, T of X over Y, is defined as the kernel of the differential map, df from Tx to the proof of Ty. And it is a classical result that this kernel is a foliation on X. This can be generalized to the following situation. So indeed, sometimes surjective maps are not that many. For example, if X has become number 1, but there are much more rational maps. So we consider a dominant meromorphic map or dominant rational map from X to Y between compact complex manifolds. Then up to blowing up this X, so we will obtain a smooth birational model X prime so that this rational map becomes a morphism. So we get a morphism from X prime to Y. Then this morphism G induce a foliation on X prime, and this foliation descend to some foliation on X. So in this case, we say that this foliation on X is induced by a dominant meromorphic map. So of course, we see that this foliation is independent on the choice of Y, because for rational maps, we can blow up Y higher, but we still have a rational map. So this foliation is very closely related to the birational geometry on X. Indeed, every foliation induced by meromorphic map is one-to-one correspondent to rational map on or meromorphic maps on X. In this situation, so if foliation is induced by meromorphic map, and if X is a projected variety, we say that this foliation is algebraically integrable. Now let X be a compact complex manifold, and let F be a foliation. So I will denote X0 be the largest open subset, where F is a subbundle of Tx. And I will call this open subset the regular locus of F. So we are now interested in how to characterize a foliation which is induced by meromorphic map or algebraically integrable. This consideration is quite classic, and at least it can date back to 2001 in papers of Bost and Bogomolov-Kähler. So I consider the product Z equal to X times X, and then I let delta be the diagonal in this product. Then there is a foliation defined on Z, which is written as this one. So the P2 of F minus 1 intersect P1 minus 1, 0, where P1, P2 are the natural projection onto the vectors. So we can look at this picture here. P1 is the vertical projection, and P2 is the horizontal projection. So these two coordinate axes, they correspond to vectors of X. And in the middle, there is a diagonal. So we see that this foliation G is vertical because it is contained in the pullback of the zero foliation or foliation by point from the first vector. So it must contain in the relative tangent of this vertical direction. So G, I put an arrow here showing that G is indeed vertical. And by construction, if I restrict G to any vertical fiber here, it is isomorphic to the foliation F. So this G is closely related to the initial foliation F. And now I denote this Z0 equal to X0 times X0. So this is the open set where G is regular. So G is a subbundle of Tz on this Z0. And I let delta 0 be the intersection of delta with Z0. Then, of course, just here, G is regular on Z0, and it is transversal to delta 0. So we can visualize on the picture. So delta is in this diagonal direction, and G is in this vertical direction. So they must be transversal. Now, we call this analytic graph or formal graph, gamma 0 of F. So the graph is defined inside the product. So it is the union of local leaves of G passing through the points of delta 0. And it is a locally closed submanifold of X times X in the Euclidean topology. So in particular, this gamma 0 is smooth. It is a manifold. But it is kind of very small and definitely in general not exist in the Zariski topology. So it is only defined in this Euclidean topology. So we can visualize this graph kind of on this small picture. So at every point of the diagonal delta 0, the foliation is regular and transversal to delta. So we can integrate locally this foliation and we get a lot of small leaves, local leaves around this point. So I will just collect these local leaves and then we collect all of them together. So by patching everything together, you'll get this shaded region, which is around this diagonal. And this shaded region is the formal graph or analytic graph. So in this picture, this seems to be a tubular neighborhood of this delta knot. But in general, this is not true. Indeed, here, because we cannot have too many dimensions in this two-dimensional picture, so we cannot see the real shape of this formal graph. Indeed, we can compute easily that the dimension of the graph gamma 0 is equal to the dimension of x, the dimension of the diagonal, plus the rank of the foliation. So it is strictly smaller than the dimension of z, which is x times x, if the foliation is not the entire tangent. So this is the definition of analytic graph. And as I mentioned earlier, this foliation G is closely related to the foliation F. And one aspect is the following one. We can consider the normal bundle of this delta knot inside gamma knot, this gamma knot. So we can visualize the normal bundle of this diagonal inside this shaded region gamma knot. And we can compute that this normal bundle is indeed isomorphic to the restriction of the foliation F on the regular locus x0. So now with this viewpoint on this analytic graph, the foliation is translated into some normal bundle. Now the criterion is the following one. The foliation F is induced by a meromorphic map if the Zariski closure of gamma 0, or this shaded region inside this x times x or inside z has exactly the same dimension as gamma 0 itself. So this is the criterion when the foliation is induced by a meromorphic map. To prove this, we use the argument of Hilbert schemes or Cho variety for projective varieties, and for Kähler varieties, we use the analog, which are Duarte space and Barley space. So we translate this problem when a foliation is induced by a meromorphic map to the following problem. So we have some locally closed submanifold gamma 0, and we want to investigate whether its Zariski dimension has the same dimension as itself. So which is written here. So let X be a compact complex manifold, and let S0, which is gamma 0 in the previous slide, let S0 be an irreducible locally closed submanifold. And I let M be the Zariski closure of S0. We want to see if dimension M is equal to dimension S0. So in the projective setting, if the equalities hold, we say that S0 is algebraic. Indeed, in this case, we know that S0 is one local branch of algebraic subvariety of X. So in this case, we say S is algebraic. Of course, in general, we will not have equality for this dimension. In general, the Zariski closure may be much larger. For example, I let x equal to P2, I let x0 equal to C2, and I let S0 be inside this C2 as the graph of an entire function on C, phi. Then this Zariski closure of S0 inside P2, M, it is a curve if and only if phi is a polynomial, because S0 is a curve. So if and only if phi is polynomial. And this is by Chou's theorem. Chou's theorem says that every closed analytic variety in the projective space is an algebraic subvariety. So M is a curve. We must have that phi is a polynomial. So we'll see now when this equality may hold. So we are searching for a criterion so that dimension M is equal to dimension S0. So in the following two slides, we will use the Bost's method in a paper of Bost in 2001, which is the same year of the paper of Bogomolov-McQuillan. They consider the same situation. Indeed, recently, Professor Cassini told me that this Harshon already have this similar consideration in 1968. So the situation is as follows. So Bost, Bogomolov-McQuillan, and Harshon, in their consideration, X is always projective. So I assume X is projective. So there is an ample line bundle L on X. And now I take a general point X, small x inside S0. Then for any integer D and I, we can define this space EID. So it is a vector subspace of the space of global section of L of power D. And this I describes the following property. So a sigma, a global section, is inside EID if and only if the restriction of sigma on S0 vanishes at the point X with order at least I. So I emphasize that we consider the vanishing order of the restriction. So I is the vanishing order and D is the power we raise for the line bundle L. So for a given D, if we increase the vanishing order, there will be fewer and fewer sections. So we have this decreasing sequence. And we can take the limit of this decreasing sequence. I will denote this by E infinity D. So by definition, sigma is a global section in LD, which is inside E infinity, if and only if its vanishing order along while restricted to S0 at the point X is infinity. But for algebraic or analytic functions, the vanishing order at a point is infinity if and only if the function is entirely zero around that point. So a section is in E infinity if and only if it vanishes exactly along the whole S0, because S0 is connected. And since the vanishing locus of sigma is a Zariski closed set, this implies that this Zariski closed set must contain the Zariski closure S0 of M, which means that sigma is indeed the section of LD which vanishes along M. Now the characterization is the following one. So S0 is algebraic if and only if there is a number lambda such that this sequence becomes stationary and equal to this E infinity whenever I over D minus 1 is greater than or equal to lambda. So to fix D, if the vanishing order is higher than lambda D, then the sequence becomes stationary. So we can visualize a little bit the reason for this argument. So assume that we have a quality between S0, dimension S0 and dimension M. And I consider some sigma which is in EID, but which is not in E infinity. So sigma is not entirely zero along M. So I can restrict sigma on M. It is a non-zero section of this L over D restricted to M. So I call this sigma prime. So I have a global section of some ample line bundle, and the vanishing order of sigma prime at X is indeed equal to the vanishing order of sigma restricted to S0 at X, because S0 and M, they are the same around X. So the vanishing order of sigma prime at X is I, at least I. Then we can obtain that I over D is bounded from above by some constant, only depending on X, M, and L restricted to M. This is related to the Caesaride constant. So this is why we should have this characterization. And this is the situation of algebraic or projective varieties. So what I'm going to do is to extend this method to the setting of Campana-Paun varieties. And the reason is the following observation. So I consider the same situation before. I want to use a different language without using ample line bundle and without using vanishing order. To do this, I take some sigma, which is in H0 L of D. Then sigma will induce a Hermitian matrix H on L, which might be singular, which means that which might have infinity length, as follows. So I assume that rho is a local section of L. To define a matrix on this L, we only need to determine the length of this rho, this local section. So we can do this. So we take the power D of this local section, and I can divide this rho D by sigma. So above is a section of LD, below is a section of LD. So their quotient is indeed a section of OX, which means that this is indeed a local meromorphic function on X. So we can consider their absolute value. And we define the length or the matrix of rho. The length of rho is equal to rho of power D over sigma, the absolute value. And then I take the dth root, positive dth root. So we can start from a global section and define a singular Hermitian matrix on this ample line bundle. Now I take some Kähler form omega in the class of C1L. So because C1 L is ample, that's just equivalent to say that its cohomology class, first Chen class, contains some Kähler form. Then in the language of compared analytic geometry, this singular Hermitian matrix H will give an omega pxq function phi. So I will define this omega pxq a little bit later. And if you write down explicitly with this construction, we can see that phi can be written in this shape. Phi is equal to 1 over D log of the absolute value of sigma plus O1, something bounded. So with this interpretation, we no longer need this line bundle, ample line bundle. We just need some Kähler form omega. And global sections, they are replaced by omega pxq functions. Now for the vanishing order. So in the Priest criterion, we need to consider vanishing orders. In our new interpretation, the vanishing order of sigma restricted to S0 at the point X is exactly equal to the known number of this omega PSH function restricted to S0 at the point X. More precise, it is this one. So we have this sigma is in EID, and I assume that it's not in EI plus 1D. So its restriction is has exactly vanishing order I. But then here that means that the low number of this log function at restricted to S0 at X is equal to I. And then I need to divide this 1 over D. So I remove this D, I add this D minus 1 here. So here we see that with this notion of PSH function, we can consider all I and D together. Because when we consider this low number, this I, D minus 1, this ratio appears naturally in this low number consideration. So with this new interpretation, we no longer need vanishing order. So we expect to adapt Bost's method in the setting of a Kähler manifold with this new language. So I will recall very quickly the notion of PSH functions. So for this, we need to first introduce a little bit the notion of currents. So there are differential forms which have a distribution as coefficients. So they are dual to the differential form of complex supports via integration. And next, we will consider purely subharmonic functions. This is a topic in complex variables. So a real locally, roughly speaking, a PSH function is defined as follows. A real locally integrable function on an open domain of Cn is PSH if this DDC phi is a positive 1-1 current, and if phi is upper semi-continuous. Here DDC is this operator. So we have some function or a generalized function or a distribution, and we take the DDC or this partial bar, and we are going to have something of type 1-1. So it is PSH if only if this current is a positive current. So using local charts, we can define PSH functions on any complex manifold. So we only require that it is locally PSH. But however, there is a maximum principle for PSH functions. So by maximum principle, every PSH function on a complex manifold must be a constant. So there are not so many PSH functions on a compact manifold. However, we can consider a little bit more generalized notion. And in this case, we will have plenty of them. So we first fix some closed real smooth 1-1 form on a complex manifold X. Then a function phi is called theta PSH if the DDC phi plus theta is a positive current. So in this case, we will call that phi is Gaussian PSH, or it is theta PSH if we need to emphasize the letter theta. So this is just like in a compact manifold, there are not so many global holomorphic sections or global holomorphic functions. There are only constants. But if we consider line bundles on complex manifold, there may have plenty of global section. So this is an analog or the idea behind one idea behind the Gaussian PSH functions. We can consider there are PSH functions inside some line bundles. So once we know the notion of PSH function, we can define these low numbers. So there is a very precise definition here, but we are not going to use this one. So indeed, we are going to use the expression for the low number for PSH functions with analytic singularities. So phi is said to have analytic singularities around a point X. If locally, we can write this phi as the log of some sum of squares multiplied by some positive real number and with something bounded to add. And here, for the summons, every GI is a holomorphic function around X. So this is a PSQ function, and if a function can be written in this shape, we will say that phi has analytic singularity. So for functions with analytic singularities, we can use the definition of the known number to compute. Then the known number of this function at a point x is exactly equal to this alpha, the leading coefficient, multiplied by the minimal vanishing order of these functions g1 to gr at x. So here we see that the known number is closely related to the vanishing order of holomorphic functions. So we can write a table here. So in the algebraic setting, we consider divisors and divisor classes, and there is some n1x, the vector space generates by the numerically equivalent divisors, and there are ample divisors, and NAF divisors or NAF classes, and pseudoeffective divisors or pseudoeffective classes. So in the Kähler setting, we no longer consider divisor, we consider current. Indeed, every effective divisor will give us a positive 1-1 current by taking the integration on the smooth part of this divisor. And we will consider the cohomology class of these closed currents. And we will consider the space of these cohomology classes. They are this H11 of XR. So this is given by the Hodge theory. So these are the 1-1 real, the class of closed 1-1 real forms. And for ample divisors and ample classes, we consider Kähler class instead. And for NAF class, they are just the limit of Kähler classes inside this H11. And for pseudo-effective class in H11, it means the class of some positive 1-1 current. And then for numerical equivalence of two divisors, we'll write two classes, they are cohomolog. So alpha and beta, if there are two currents, they are cohomolog if they differ some DDC phi. Phi is some, say, L1, locally L1 function. And if we want to investigate the vanishing order of a section of inside a line bundle at a point, we consider the known number at a point instead. And for the dual part, dual part of this n upper one, we have this n lower one. So this is the space, vector space generated by curved classes. And on the Kähler setting, we consider this Hn-1, n-1, xr. So n is the dimension of x. So with this comparison picture, we can finally kind of generalize Bost's criterion in this Campana-Paun manifold. But indeed, I did not prove exactly the same characterization at this stage. I proved some weaker version. So let me introduce it. So let X omega be a Campana-Paun manifold, and let S0 be a locally closed irreducible submanifold of smaller dimension. And I assume the other side. So I assume that S0 is Zariski dense, which means that the Zariski closure of M of S0 is equal to X. So which is the very negative side of that dimension S0 is equal to dimension M. So dimension M becomes the largest possible. It becomes X.
I'm sorry, can I ask a stupid question? So what do you mean by Zariski closure in this analytic setting?
Okay, thank you. So everything is compact. So Zariski closure means that the largest closed analytic subset of X, which contains S0.
Okay, thank you.
Okay, thanks. Okay, so I will prove the negative of this Bost criterion, which means that the decreasing sequence of this global section will be stationary starting by some point ID minus one is larger than some lambda. So I need to prove the negative part, the negative of that assertion. So which means that I need to prove that for any lambda positive, there should be some EID with ID minus one larger than lambda, such that that EID is not the E infinity. So we translate that with the language of currents at a number in the following theorem. So this is I call this a simple version. So I let X be inside S0 be a general point. And I assume that this S0 is Zariski dense in X. Then there is always omega PSH function phi with analytic singularities such that phi restricted to S0 is not identically minus infinity, and that the Lenung number of phi restricted to S0 at the point X is greater than or equal to lambda. So we can do this because the restriction is not minus infinity entirely on S0. So its restriction on S0 is a non-trivial omega PSH function. So we can compare this with Bost's criterion, right? So in Bost's criterion, he says if S naught is algebraic, then there is some mu such that if ID minus one mu is greater than this mu, then I is infinity. So here, that this sigma is in this EID minus one. Here, in this Bost, the I is the vanishing order of a global section of the sigma restricted to S0 at X, and D is this power of L. And with our previous translation or previous dictionary here, this just means that sigma is become some, so L is become omega. L becomes omega, and sigma becomes phi. And phi is restricted to S0 is minus infinity entirely, just means that sigma is entirely zero along S0. And this vanishing order divided by D, so this guy is just this Lenung number. So with this dictionary, we see that this is exactly the negative negativity of the Bost criterion. So there is some sigma with this ID minus one larger than lambda, such that sigma is not entirely zero on S0. So to prove this, there are two parts. So firstly, we apply Dema-Yi's mass concentration method introduced by Dema-Yi in 1993. And it relies on Yao's theorem on these Monge-Ampère equations. And we can construct some omega PHQ function, which has a very large restriction Lenung number. Here, we essentially use the assumption that S0 has a smaller dimension. But this omega PHQ function may not have analytic singularity. So for the second part, we use Dema-Yi's regularization of current, so introduced by Dema-Yi in 1992, to get this analytic singularity. So we may get some smaller Lenung numbers, but not much smaller. So this is due to Dema-Yi. So by combining these two methods, we can obtain this simple version. But we will use a more general version for our objective. So again, X is omega compact Kähler, S0 an irreducible locally closed manifold of smaller dimension, and assume that S0 is Zariski dense. And I assume some further data. So I assume that C is an irreducible compact submanifold of X with dimension C is equal to dimension S0 minus 1. And I suppose that S0 contains an open subset C0 of C. And furthermore, I assume two technical assumptions. But we will check that these assumptions are satisfied in our application. Then there will be an omega PSH function phi with analytic singularities, such that this restriction number is greater than or equal to lambda for all point x on this C0. So indeed, we are kind of going to apply this version to the setting of analytic graph, because our goal is to prove some foliation is algebraically integrable. So which is equivalent to prove that this shaded region has the same dimension as its Zariski closure. So in this situation, we see that this shaded region, which is S0, it contains the Zariski open of some closed Zariski subset. So the closed Zariski subset, which is the diagonal here, is the C here. And the C0 is just this diagonal with this empty point removed. So this is the regular locus of the foliation. Of course, we do not have this dimension equality, but we only need to blow up this x times x, this product at this diagonal, and we are going to have this dimension equality. So indeed, we are in this situation, so we will need this a little bit more general version of the previous criterion. So with this, with this picture in mind, we are going to prove this one. So the proof of this one is very close to the proof of the simple version, just with a little bit more work. So these are two criterion to see whether, or two properties that S0 is Zariski dense in X. Now I will introduce two algebraicity criterion. So now I will determine that when this S0 has the same dimension as its Zariski closure. So let x omega be a compact Kähler manifold and S0 be an irreducible locally closed submanifold, small dimension. I assume that it contains some Zariski subset C0 of C, where C is closed analytic submanifold of X. And I assume at the first stage that C has one dimension less than the dimension of S. And I assume some two technical assumptions as before, but now I add this assumption. I assume that the conormal bundle of this C0 inside S0 extend to a line bundle on C, such that this line bundle is not pseudoeffective by adding any dimension, adding any divisor class supported in this complement. So in other words, more or less, I say that the conormal line bundle is negative. Then S0 will have the same dimension as its Zariski closure. So this is the first one. I assume C has one dimension less than S. In the second criterion, I no longer assume that C has one dimension less than S0, but I require that the complement of C0 has a codimension at least 2 inside C. And now, before it was conormal line bundle. Here, now it becomes conormal bundle, which might have rank larger than 1. So I require that this conormal bundle extend to some reflexive coherent sheaf N star, such that this N star is a non-pseudoeffective coherent sheaf. Then S0 will have the same dimension as its Zariski closure. So for this problem, I will blow up X along C. And then I will take the strict transform of S0 in the blow up. Then if we consider the preimage of C0 inside the strict transform of S0, we will recover this situation, right? So by blowing up some subvariety, I transform this subvariety into a divisor. So in this general situation, by blowing up C, we'll reach the first situation. So I think I'm running out of time. So once we have this previous criterion, this analogy of Bost's methods, we can adapt it to prove the algebraicity criterion one here. So which means that C has one dimension less than S0. So once we prove this, we apply this criterion to the situation of the analytic graph of a foliation, which is this picture before. And we can prove that if on a compact Kähler manifold X omega, if F is a foliation such that F dual is non-pseudoeffective, then F is induced by a meromorphic map. So this is the key point for the uniruled criterion. So I think I will stop here. Thank you for your attention.
Thank you very much. Any questions? Could you say a little bit how you continue once you have the fact that once you know that it's realized by this meromorphic map?
Oh, yeah, thanks. So at my stage, once I obtain this meromorphic map, so I can blow up X a little bit so that this becomes a regular map, a morphism, such that X and Y, they are again Kähler manifolds. Because unirule is a birational invariant and canonical is non-pseudoeffective is also a birational invariant if everything is smooth. So now I can assume that this is a morphism from X to Y, and a two form, non-zero two form comes from the base Y. If X is not uniruled, then general fiber of this morphism is not uniruled neither. Otherwise, they will deform into a covering family of rational curves. So by induction, because the dimension of F is between dimension of X and dimension of 0, by induction, omega F must be pseudo-effective. Now, by the theory of positivity of direct images, we can deduce that this omega of X over Y is a pseudo-effective line bundle on X. So this is pseudo-effective, but omega X is non-pseudo-effective. We can deduce very quickly that omega Y is non-pseudo-effective because this is just omega X minus omega Y. So this cannot be pseudo-effective. So by induction again, Y must be uniruled on the base. So I will claim that Y is indeed rationally connected under this assumption, because if Y is not rationally connected, I can consider the MRC fibration of Y to some Z. And this also exists and called rational quotient by the work of Campana in the setting of Kähler varieties. So we can consider this composition from X to Z. So Z, if Y is not rationally connected, Z is not a point. So the dimension of Z is between 0 and X. So I repeat the same argument again. I will see that omega Z must be non-pseudo-effective and Z must be uniruled. But this is impossible because the base of MRC fibration will not be uniruled thanks to this Garber-Harris-Stars theorem. So Y is rationally connected. But if Y is rationally and Kähler, we can prove that it is projective and there will be no two form on Y. So this two form sigma on Y, this two form sigma at the beginning, which is non-zero, and we prove that it descends on Y, then it must be 0 because Y does not have two form. So this two form is 0. This is a contradiction. So we are done.
I see. Thanks so much. Other questions or comments? Okay, if not, thank you again for the talk.
Yeah, thank you. Thank you very
It was
much
very
for your
nice.
attention, and thanks for the invitation.